And thank you, Professor Siepmann, for this very interesting talk. Moving to the Q&A session. The first question we have, what metrics do you prioritize when evaluating nanoporous materials for hydrogen storage, for example, capacity versus temperature stability?
Yeah, so in many so when we are looking at materials, so like the last topic on the BTX separation, we know that we want to do it at very, very high temperatures, possibly at reactor conditions. So that means the temperature stability of the material becomes very, very important. And we are only looking for zeolites because we know that polymers, so polymeric membranes or metal organic frameworks, covalent organic frameworks, would not survive the conditions that we want to use. When we are looking at the specific case of hydrogen storage, currently these techniques are investigated at 77 Kelvin off, so almost all of the materials would have the temperature stability. And it might become a little bit tricky if one would go up to 300 Kelvin or so, which would be of interest. And so here we screened multiple materials, but then we found out that the zeolite have the higher optimal temperature, so the zeolites are definitely stable. So it's definitely I would say the temperature stability of the material we are already keeping in mind when we are selecting materials for the screening. And then we are somewhat we are hopeful that the materials will be stable at the conditions that we are using.
Thank you for the response. Moving to the next question. How do you exclude geometrically similar images during active learning? And how do you rationalize the stability of machine learning-based interatomic potential? Mostly hydrogen and carbon atoms tend to break easily at high temperatures.
Okay, so we did not use any filtering to remove similar images. And the reason is, of course, when we are doing the molecular simulation to generate images, then in the simulation, we might have a system that might have 8 unit cells, or maybe it might have 24 unit cells on a larger scale. But that means by averaging over images, we get more information which are the preferred site. So if there is a preferred absorption site, we should see loading and we should see a similar image for that system multiple times. So that gives us more importance to the image in the training. So we actually want in the training data, so in the we want to learn from these multiple images, and then we have an overall loading to which we are training. So these similar images that we have together, that we have in the trajectory, are then all averaged together into a single image. And then we are doing on the single image, which is the average loading, we are doing the machine learning. Then about carbon-hydrogen bond and the stability. So benzene is a very stable compound. So the BTX conversion typically is done at actually temperatures between 650 to maybe 800 Kelvin currently in the process. So at that temperature, meaning you clearly have some catalytic conversions in the catalyst between the different BTX components, but you are not having a massive amount of conversion that you would get into the membrane. And then, of course, once the material has, once the chemical compounds, the paraxylene has made it through the membrane, you would cool. So yes, carbon-hydrogen bonds are labile if you have a catalyst. Yes, I know that alkanes, if you give them a lot of time, they will decompose at these temperatures. But if you look what it is done in the petrochemical industry, and so a lot of the catalytic conversions where we want to go from linear alkanes to branched alkanes for gasoline productions, they're all done at very high temperature.
Thank you so much. We have many more questions, but with the interest of time, we'll take one more question. How does the addition of a third transfer box improve sampling efficiency in liquid phase absorption simulations?
Yeah, so this actually goes back to very early work by Dominic Teldisli group. They were interested in liquid-liquid equilibria and found out that the third box improves efficiency. So why does the third box improve efficiency? Simply, when you would transfer directly from a liquid to another liquid, or from a liquid to a porous material. So starting from liquid 1, we are taking a molecule out, so that leaves a cavity behind. So that means there's an energetic cost in that process, the energetic cost to create the cavity. Now we are taking this molecule and we are inserting it into liquid 2 or into the porous material. Typically, we will not have an instantaneous cavity that is of the correct size, correct shape, volume for the material. So also the inserted state of the molecule is typically a little bit higher in energy. And so there's also an energetic cost of inserting the molecule. So we have two energetic costs, and then in particular, when we go from liquid to liquid, there's not much of a difference in entropy between the two boxes. If we are going from a liquid to a vapor, we have the energetic cost for essentially, let's call it the entropy of vaporization at the moment. So we are going uphill in energy, but we are gaining a lot of entropy because we have a much lower number of particles per volume. So entropy favors the transfer. So that means when we are going into the transfer box, we have a benefit from a compensation between enthalpy and entropy that we are not getting when we transfer directly from liquid to liquid.
Thank you so much, Professor Siepmann, for these very insightful responses.